Hey guys, Ms. Getz here. I just wanted to give you a little bit of an explainer video on how you're going to use this simulation to work on your very first assignment. So this is a simulation of something called the HR diagram. HR stands for Hertzsprung-Russell. You'll learn a little bit more about that in the video, which is the second activity this week. But in this simulation, we have essentially a graph. And normally I'd have you go through this simulation and work on these questions with a group or a partner in class. Sadly, in distance learning, that's a little bit more complicated. If you are able to call up someone from IB Physics and have a little bit of work time together, looking at this graph and talking over the questions, by all means, go for it. That's something you can do virtually, but I'm going to let you decide if you want to do that. Do it on your own. But that would be a totally fine way to do this assignment. But it's something that you can also do by yourself, and I think you'll learn a lot just by playing around with it yourself. So there are a few things I'm going to point out in this instruction video, and then I have questions for you to go through to really dig into what this graph is showing and what it actually can tell you about stars. So this graph has temperature on the x-axis and something called luminosity on the y-axis. So you see it says luminosity here. I'll talk more about the y-axis in a second, but first let's look at the x-axis. So it's temperature. It's measured in Kelvin, which is the standard scale for temperature, because it's an absolute scale, so it's not degrees Kelvin. Anyway, moving on. But look at this temperature axis. Take a moment and see if you notice anything weird. Notice it says 40,000 right here, 20,000 right here, 10,000, 5,000, 2,300. Isn't that weird? It's going the wrong direction. And it goes the wrong direction kind of by convention. In the video you'll watch after going through this activity, he'll talk a little bit about the categorization of stars, and so it goes, the axis here, the x-axis goes backwards because it goes in the order of the categorization of stars. And it's just convention. It's just because astronomers started out that way, they've kept it that way. So it's kind of weird, a thing to get used to. So that means that these are smaller temperatures, these are larger temperatures. And then our other axis, luminosity, also has something kind of weird about it. So if you look at its units, I have 10 to the 0. That means 1. And this is measured in terms of luminosity of the sun. So this little L with a circle and a dot means compared to the sun. So because we live here in our solar system, we compare all other stars to our sun. We're very self-centered. And so we're going to be comparing their luminosities, how much energy they give off, how bright they are. Actually, it's not how bright they are, technically. It's the energy that they give off. But a good kind of conceptualization is brightness. But it's their intrinsic brightness. So their luminosity we're going to compare to the sun. So if something has luminosity of 10 to the 0, that would mean it has the same luminosity as the sun. OMG, that's our sun right there. So this X is actually showing you the star that it's plotting right now, and it's plotting the sun. On our luminosity axis, you can see that it goes up by powers of 10. So this is what's known as a logarithmic scale. And that is because stellar luminosities vary a lot. So 10 to the 6, that's 1 million times as bright as our sun. 10 to the minus 3, that means it's 1,000 times less bright than our sun. And 10 to the minus 4 would be 10,000 times less bright. I keep saying bright. Less luminous than our sun. It's not brightness, it's the intrinsic intrinsic power of the star. Normally we'd actually learn how to calculate luminosity, and we'd do some stuff with it relates to the temperature of the star and the size of the star. As you can imagine, something that is really, really hot and really, really big would have a higher luminosity than something that is really hot but small. But we're not going to get deep into that just because distance learning means we're scaling back a fair bit. The other thing that I want to point out on this graph is that you can move which star it's graphing. So right now it's graphing the sun, and the sun is actually going to stay there, but I can click on another spot right here. Click. And it is now graphing this spot. So it's telling me the temperature of this star. It has a temperature of 13,000 Kelvin. So if it's right here on the HR diagram, that would be its temperature. And its luminosity is almost exactly the same as the sun, because I just moved over in the X direction, and I didn't really move very much in the Y direction. So you can click around. On the iPad, you can like drag it. It's a little bit annoying to drag on the iPad, but if you just tap, and notice that it's actually showing you not only where the star is, but it's showing you how big it is too. So we have the radius. Again, it's 0.12 times the radius of the star. So again, we're very self-centered. We're going to think about it in terms of the star, our star, the sun, all the time. And then the one last thing that I want to point out to you is that it's going to ask you to plot some stuff. So you go up to plots up here in the corner, and you can plot the brightest stars in the sky. You can plot the closest stars in the sky. You can plot over both. And you can plot where the brightest stars and the closest stars, so that would be the closest and brightest stars. Which ones are those? And those are the overlap ones, which are in purple and are kind of hard to see. And I think you should be good to go. So you're going to be clicking around, making some stars. You're going to need to pay attention to their radiuses, their temperatures, and I think you should learn a lot about this graph just by playing with this simulation and answering the questions in this worksheet. Miss you all. Hope you're doing well.